We're back again in chemistry. This is chapter 5, part 1. And this chapter is endothermic and exothermic reaction. And this has something to do with chemical energy. This has something to do with energy in chemistry. Okay, this topic has something to do with energy in chemistry. But before that, let's take a look at what we mean by exothermic reactions and endothermic reactions. There are so many types of reactions in chemistry. Remember, we have decomposition reaction, combustion reaction, neutralization reaction, oxidation, the redox reaction, oxidation and reduction reactions. We have precipitation. We have so many types of reaction, right? We have so many chemical reactions take place, even in electrolysis, oxidation, reduction taking place in electrolysis process. We have so many types of reaction in chemistry. So in this reaction, we'll be talking about reactions that have something to do with heat energy, heat exchanges in reaction. Reactions that have something to say about whether heat is given to the surrounding or heat is absorbed from the surrounding. So this one has something to do with heat exchange in chemical reaction. These two types of reaction that we're looking at today, it has something to do with heat exchange in chemical reaction. When heat is given to our surrounding, when reaction is taking place and heat is being given to our surrounding, that type of reaction is called exothermic reaction. EXO, exothermic reaction. This type of reaction, the heat energy is given to our surrounding. Like example is burning. When you're burning pieces of paper, when you're burning bushes, when you burn anything, cooking. When you cooking with your cookie gas, you give it heat to your surrounding. You give it a lot of heat. You give it a lot of heat. You give it a lot of heat to your surrounding. This type of reactions are called exothermic reaction. Exothermic reaction, neutralization reactions. All these type of reactions that gives heat to their surrounding, these type of reactions are all called exothermic reaction. Reactions that give heat to the surrounding. You can think of so many reactions taking place where heat is given to the surrounding. So many reactions taking place where heat is given to the surrounding. Such reactions are called exothermic reaction. Now, we say in general, but the type of reaction that takes heat from the surrounding is called endothermic. The type of reaction that take heat from the surrounding is called endothermic reaction. A good example is photosynthesis. The sun energy from our surrounding is taken by the leaf and by the plant and is made use of to photosynthesize and make food for us, to make glucose, to manufacture glucose and produce oxygen as well. So this type of reactions are called endothermic reaction. Exothermic reactions are reactions that take heat from our surrounding. They absorb the heat, they take the heat and make use of the heat from the surrounding. Now, in order to characteristically explain this concept, let's start with the chemical reactions taking place. We say chemical reactions whenever we take one element of one or atoms of element to react with other atoms of another element, we produce another product. Either we make a compound is produced, or molecules of compounds are produced. Now, when this happens, then we say that this type of chemical reactions, they occur so that element can achieve a more stable energy state by gaining a full outer shell of the electron. Why do elements react? Why do elements react? Why do elements react even in the first place? Why do atoms react? Atoms react because they are not stable. Why? The outer shell, in their outer shell, every atom has, for example, sodium atom, the electrons are arranged in the configuration, electronic configuration, 2,8, this. We have the board? No? Okay, 2,8. We have, for sodium, for example, we have 2,8,1, right? 2,8,1, right? We have 2,8,1 for sodium. Now, if you have 2,8,1 for sodium, the first shell will hold what? The first shell will hold what? 2 electrons. The first shell of the atom will hold 2 electrons. The second shell, I'm trying to open the board, okay? I'm trying to open the whiteboard so that I can draw it and show you. The first shell will hold 2 electrons, and the second shell will hold 8 electrons. And 8 is the maximum electron that a particular shell can hold. 8 is the maximum electron that a given shell can hold. And when you have 8 in your outermost shell, it means you're stable. You don't need to react. The reason why atoms react or elements react is because their outermost shell are not usually 8. When your outermost shell is 8, you don't need to react. For example, elements like neon, a noble gas, neon, which has atomic number 10, they don't need to react. They are all reactive gases. The noble gases, the group 8 or group 0, they are all reactive, right? They are all reactive, right? They are all reactive. Why? The reason why they are all reactive is that neon, the first shell has maximum of 2, which is the normal rule. Every first shell must hold only 2, cannot hold more than 2. Every first shell will hold only 2 electrons. The second shell, the maximum it can get up to is 8. Now, once he has 8 in his outermost shell, that atom does not need to react. It's already like super okay. It's already super okay. The atom has got what it wants. It has what it takes. It doesn't need to react, okay? It doesn't need to react. It has what it takes. For example, if you have sodium, I will use their symbol, okay? Sodium is Na. Okay, so the atomic number is 11 for sodium. The atomic number is 11. And the mass number is 23. Okay, so if you draw the first shell, the electronic EC, electronic configuration EC, is equal to 2 for the first shell. You can say plus, okay, or you use comma. Usually I prefer using comma. Then the second shell, maximum of 8, since it still has, out of this 11, if you take 2 out, 9 remains. So the second shell can hold 8. And then the last shell can hold 1. It's only 1 remaining for the last shell because it's 11. 2 for the first one, 8 for the second one, and 1 for the last shell. So if you draw that, if this is our first shell, let's say this is the electrons, and then here is the nucleus. In the nucleus, you have the proton and the neutron. In the nucleus of the atom, you have the proton and the nucleus inside the nucleus of the atom. Proton and the neutron inside the nucleus of the atom. So the first shell, the electrons are 2. Then the second shell for sodium, the electrons are what? 8. 8. The electrons are 8. So we try to draw that. The last shell, electron is only 1. The last shell, the electron is only 1. It has only 1 electron in the outermost shell. Remember, sodium has only 3 shells. The first energy level is the first shell. It has 2 electrons. The second one has 8 electrons. And the third one has 1 electron. The third one has 1 electron. The third one has 1 electron. So because it has 1 electron, it's unstable. This shell is supposed to be filled up 8. Supposed to be complete 8 in order for the atom not to react. Once an element or an atom has 1 in the atmosphere or 2 in the atmosphere or 3 in the atmosphere or 4 in the atmosphere, or 5 in the atmosphere, or 6 in the atmosphere, or 7 in the atmosphere, it will react. It will react. It will react. Unless it has 8 in the atmosphere, like argon. Argon doesn't need to react. Argon doesn't need to react. Argon is AG or AR? AR. You sure? Okay. We have 18, right? Atomic number is 18. That's number of protons is 18. So if the number of protons is 18, you see here you have 2 in the first shell, you have 8 in the second shell, that's 10. 2 plus 8 is 10. Then in the third shell, you have another 8. That makes it 18. Since argon has 18 electrons and the last shell is complete 18, once your utmost shell, the last one, the utmost shell is 8, the electrons in the utmost shell is 8, then that atom does not need to react. It's already stable. The reason why we are saying this is that atoms react because they have unstable state. The moment why they have a stable state is because the electrons, the number of electrons in the atmospheres are not 8. If you have 8 electrons in your atmosphere, then you will be stable and you don't need to react. You don't need to react with another element or another atom to form a compound or to form anything. You are already unreactive because you are already stable. The reason why atoms react is because they are not stable. They don't have complete electrons in their atmosphere. So they have to combine with other atoms in order to have complete electron in the atmosphere. So that's the reason. That's the first part I explained. Now, they do this by doing what we call the chemical bonding. Atoms, they stabilize themselves by carrying out what we call chemical bonding. You know, we have the basic one for your level now. We have the ionic bonding. Atoms do this by undergoing chemical bonding. The first one is ionic bonding. The second one is covalent bonding. The third one is metallic bonding, covalent bonding. The third one is metallic bonding. And the fourth one is hydrogen bond, covalent bonding. Then the third one is metallic. Metallic bonding. Metallic bonding. And then at higher level, we do hydrogen bonding. Okay, so this is how atoms are able to stabilize themselves. Atoms are able to stabilize themselves by carrying out bonding with other atoms in order to find in order to complete their outermost electrons 8, in order to make their outermost electron 8, and then they will be stable. Because if your outermost electron is not 8, then you will not be stable. So you need this in order for you to be stable. You need this in order for you to be stable. Ionic bonding is the type of bond. Okay, this is not the topic we have, so we shouldn't so much dwell on this. But remember, ionic bonding is the type of bond between metals, a metal and a non-metal. The bond that happens between a metal and a non-metal. Where the metal, like sodium, we donate. Chlorine is a non-metal, for example, and chlorine has 17 in there as atomic number. It has 17 as atomic number, and the mass number is 35.5. The average, because it's an isotope. Because an isotope is 35.5, meaning an isotope have more than one mass number, so we can find the average. Okay, so chlorine has atomic number 17. It means the number of protons is 17 and the number of electrons is 17. Remember, the number of protons and number of electrons are same. That's why an atom is same in an atom. Number of protons and number of electrons are same. That's why an atom is said to be electrically neutral. That's why an atom is said to be electrically neutral. So we have number of protons equal to number of electrons and equal to 17. Equal to 17. Is that okay? Okay, so now this one, chlorine has 2,8,7. So because it's 17, 2 plus 8 is 10 plus 7 is 17. So chlorine is looking for one atom. So sodium has one extra. So sodium can give 1 to chlorine. Sodium can give 1 electron to chlorine. And then that kind of bonding where you donate, whereby you donate, you give, you donate, you lose or you gain, is called ionic bonding. This one we lose 1 electron to this one, and that type of bonding is called ionic bonding. Covalent bonding is different. Covalent bonding, you don't give your outermost electrons to any other atom, but you share. You share. This one happens between non-metals. Covalent bonding happens between non-metals. So it's like I have some in my atmosphere, you have some in your atmosphere, we share. This one is about sharing. Covalent bond is about sharing. Covalent bonding is about sharing. Ionic bonding is about donating or giving. This one is sharing. Sharing atmos electrons. This one is about sharing. This one is transfer. This one is transfer of electrons. Transfer. Then metallic bond. Metallic bond has something to do. This one happens between metals. The electrons in metals, ability of the electrons in metal to move freely. Okay, electrons movement in a metal. Electrons movement in a metal. So that's metallic bond. Okay, now let's move on quickly. So we say atoms, they do this in order to be stable. They do this by carrying out what we call chemical bonding. We've just a little review on the chemical bonding, okay, because we've done this before, right? We just have a review on them. Now what happens is that the old bonds will be broken and new bonds will be formed when reaction takes place. For example, when chemical reaction takes place, let's take a look at this. When the reaction takes place, okay, the old bond will be broken. For example, hydrogen is H2, react with oxygen, hydrogen H2, react with oxygen O2. Okay, they are diatomic. These are the diatomic gases. Okay, that's why you see 2. Okay, then this will produce what we call water. This will produce water. Now this water, okay, we can balance it anyway. We can balance. This will produce water, right? We balance this chemical reaction. The first thing you do is to balance the chemical reaction. Now, if here oxygen is 1, but here oxygen is 2, if I put 2 behind it, let's use a different notation. If I put 2 behind this place, it becomes 2 molecules of water, right? Now 2 molecules of water. The atoms of hydrogen is now 4. 2 times 2 is 4. 4 atoms of hydrogen. 2 times 1, here is 1, remember, even if we don't write it, here is 1. 2 times 1 is 2, oxygen is now 2, so oxygen is balanced. But hydrogen is 4, it's no more 2. So what should we do? We come to where hydrogen is, we put 2 behind it. You see, 2 times 2 now oxygen is. So hydrogen here is 4 atoms, here oxygen is 2 atoms, here hydrogen is 4 atoms, and oxygen is also 2 atoms. So the equation is balanced. So both in the reactor side and in the product side, we have same number of atoms for each of them. So this is the balance. Now let's do something again. We say the bonding in chemical reaction. In chemical reaction, the old bond will be broken down so that new bond will be formed. This is the old bond. Hydrogen gas is the old bond. If you put the state symbol, here we have a gas. Here is also a gas, and here is a liquid. Here is a liquid. Okay, here is a gas, oxygen is a gas, hydrogen is a gas, and here is a liquid. Now, what happens in chemical reaction is that this bond will be broken. You know hydrogen bond? You know the hydrogen bond is like this. You know, right? Let's take the hydrogen bond, orange. Okay. Now, let's take the hydrogen bond. The hydrogen bond is like this. It will break like this, singularly. To break singularly, H to H. This will be broken down into H to H, single bond. Hydrogen to hydrogen, single bond. This will be broken. Okay? This H2 is broken down into this. This H2 is broken down into 2. Because there's 2 at the back, we can put the 2 here, right at the back here. We can put the 2 right at the back of this one. So we put 2 here. meaning two of this bond. There are two of this type of bond, okay, for hydrogen. Now oxygen, we now say plus. Let's do the bond for oxygen. Probably we change the representation to something different. For oxygen, we can take this one. It's close, super close. For oxygen, let's take a faint. No, let's take this one. Okay, for oxygen, we take this one. Let's say for oxygen, oxygen to oxygen is double bond. I can also explain why oxygen to oxygen. We can explain why oxygen to oxygen. Why is it double bond? But hydrogen to hydrogen was a single bond. Now here, oxygen to oxygen is double bond. During the sharing, they share 2 electrons. They both share 2 electrons in the atmosphere. You know, oxygen is 8. Atomic number is 8. So the electronic configuration is 2 for the first share and 6 for the second share. It's looking for 2 electrons. It's looking for 2 electrons, right? It's looking for 2 electrons in order to. But if you're looking for 2 electrons, you will be double bond. If you're looking for 3 electrons like nitrogen, you'll be triple bond. If you are looking for 1 electron, you'll be single bond. This one is looking for 2 electrons to complete. It needs 2 electrons in order to complete 8. Since it's looking for 2 electrons, so it's going to be double bond for hydrogen. Is that okay? For chlorine is single bond. Hydrogen is single bond. Oxygen is double bond. Why is this one single bond? Because chlorine is looking for 1 electron to make it 8. It has 7 in the atmosphere. It's looking for 1 electron. So chlorine to chlorine will be a single bond. Chlorine to chlorine will be a single bond. But what of nitrogen? What of nitrogen? Nitrogen will be, what will be the bond of nitrogen? Nitrogen will be a triple bond. For nitrogen, it will be a triple bond. Why? Why is that so? Because nitrogen will be a triple bond because it's looking for 3 electrons in order to complete its octet rule, to complete the 8 electrons in the atmosphere. Because it's looking for 3 electrons in order to, because atomic number of nitrogen is 7. So the first share will hold 2, the second share will hold 5. The first share will hold 2 electrons, the second share holds 5 electrons. Now it's looking for what? 3 electrons. It's looking for 3 electrons. You need to gain 3 electrons. Since it's looking for 3 electrons, the number of electrons that is needed for you to complete, this thing determines your bonding. Determines your bonding with yourself. Determines your bonding with yourself, okay? So since hydrogen and nitrogen is looking for 3 electrons to complete 8, therefore it will be nitrogen to nitrogen triple bond. Oxygen is looking for 2 electrons to complete 8. It will be oxygen to oxygen double bond. This is called double bond. Oxygen to oxygen double bond. So because of there's no 2 at the back, so we're not going to put bracket and put 2 here. There's no number here during the balancing stage. So this is what we have. And then the product. Now let's represent the product. What we have in the product, let's say we have water is O to H. Okay, for water is let me see, OH, one O, 2H. Okay, to another side like this. See, this is the bonding in water. Okay, let's see the bonding in water. Now let's draw it here. So we can have our O here, our oxygen, and then we have the bonding this way to hydrogen. Oxygen is looking for 2 atoms, right? It's looking for, so 1 atom from here, and then another single bonding on this other side to 1 hydrogen. To 1 hydrogen. That's why it's H2O, 1 oxygen. But because there are 2 molecules, we can put a bracket and put 2 behind. Because there are 2 molecules, we can put a bracket and put 2 behind. There are 2 molecules of water. So we put 2 behind. Okay, there are 2 molecules of water, so we put 2 at this junction. We put 2 here. So this is what happens. Now, first of all, they need energy in breaking the bond. This old bond has to be breaking, old bond. These ones are called old bond. Energy of the reactants are called the old bond. Energy of the reactants are called the old bond. Old bond. These are called reactants, okay? These are called reactants. Okay, we know that. We don't need to waste our writing ink. So these are called the product. We know this. This is called the product. So they break the bond. The hydrogen bond will be broken and oxygen bond will be broken. The energy needed to break this bond is called the energy in. energy in. The energy needed to break this bond is called the energy in. Energy into the reaction. Energy in. Then the energy needed to form new bond, because here they will form new bond. You can see one oxygen atom, we take 2 hydrogen atoms. Because hydrogen now we have what? How many? 4. One oxygen atom, we take 2 hydrogen, which is this. One oxygen taking 2 hydrogen. And this one, because it's twice, meaning there's another one like this. There's another one like this. Okay? Another one oxygen taking like this one. Like another oxygen taking 2 atoms. That's what is happening here. That's why we put 2 at the back. Meaning it's twice. When you say 2 apples, meaning you have 2 apples, right? Okay, so it means that you have 2 of this bond. So one oxygen take 2 hydrogen atoms, because there are 4 hydrogen now. 2 times 2. These 2 outside multiplied by these 2 inside. 2 times 2 is 4. One oxygen atom take 2 hydrogen atoms. This second oxygen atom takes another 2 hydrogen atoms. That's the forming of new bond. This is new bond. New bond. First of all, they need energy to break the old bond. And then they need another energy to form the new bond. This is called the new bond. Now, the energy for breaking the old bond is called the energy into the reaction. Energy in. And then the energy for forming new bond is called the energy out. The energy for forming new bond is called the energy out. Now, in chemical reaction, the energy change is calculated by simply saying delta energy is equal to the energy in breaking the old bond. This is equal to the energy in breaking the old bond. That's the energy of reactant. That's the energy of the reactant. Energy in breaking the old bond. Okay, which we call the energy in. So we're going to calculate the energy in, the total energy in, and the total energy out. And then we can now find the energy change, which we're going to do in this chapter. Okay, so the energy in forming new bond, the energy in forming new bond, the energy in forming new bond is equal to, the energy change is equal to energy in breaking old bond minus energy in forming new bond. The energy in forming new bond is called the energy out. The energy in forming new bond is called the energy out. So, the energy change is equal to energy in minus energy out. So this is the formula for calculating the energy change in chemical reaction. So we're going to look for a table that shows all the value of the bond. H to H bond, they will give us the energy value. And O to O double bond, O to H single bond. So we can calculate the energy change. This is always in IGCSE questions, okay? Calculating the energy change from a chemical reaction. Okay, like sometimes they give you this type of reaction. Hydrogen hydrogen react with ammonia, react with nitrogen to form ammonia. Hydrogen react with nitrogen in a reversible manner to form ammonia. They always, in IGCSE paper, they always bring this question. They want you to calculate the energy change. They want you to calculate the energy change. So here you balance. You have 2. Hydrogen here is 2. So if I put 2 here, hydrogen will be 6. You have to balance. Always balance your chemical equation. Always balance. If I put 2 here, hydrogen will be 6. Nitrogen is 2. So nitrogen is 2, hydrogen is 6. So for hydrogen to be 6 on the reactant side, I put 3 here. So 3 times 2 is 6. So once you have a balanced equation, you break down the bond. Okay. You write the bond breaking, energy in breaking, forming new bond. You have H to H single bond. You have H to H, energy in there, breaking old bond. Sorry, this is energy in breaking the old bond. Okay, you have to H to H single bond, and then here we're going to have what? we're going to have multiply by 3, right? Multiply by 3, we take a different color. Multiply by 3, here I put 3 here. There I say plus. What we have here, hydrogen to hydrogen, this is N to N, triple bond, right? Triple bond. Triple bond. And it's just one of it, N to N triple bond. Then we find our, you have N. If you have N here, let's take a different color. Let's take something like blue. Okay, if you have N here, it's bonded by 3 hydrogen atoms. One nitrogen atom is bonded by 3 hydrogen. So here we can have one here, one here, one here. So we can have one this way, and one this way. So bonded here with hydrogen. Bonded here with hydrogen. Bonded here with hydrogen. So this is ammonia. This is bonding in ammonia. Okay? That's why it's triple bond. One bond to one hydrogen here, one bond to one hydrogen here, one bond to one hydrogen here. So it's complete 3. So 1 to 1 hydrogen, 1 to 1 hydrogen, 1 to 1 hydrogen. But multiply by what? We go to multiply by, because 2, there's 2 outside. So there's twice of this energy. So I've calculated there's twice of this energy. So here we go to multiply by 2. Whatever we get for this bonding, we go to multiply by 2. We go to multiply by 2. So the bond, you can see here, you have one bond here like this, nitrogen to hydrogen. You have another bond this way, nitrogen to hydrogen. You have another bond this way, nitrogen to hydrogen. This is how they bond. Okay, this is how they bond. Okay, and then you multiply by 2. So these are the energy for this, your energy in. Energy of reactant is the energy in. Energy of your reactant is the energy in. The energy of your product is your energy out. Energy of your product is your energy out. Energy of your product is your energy out. Okay, then the energy change in the chemical reaction is delta E. Energy change in the chemical reaction is delta E. Delta E is equal to energy in minus energy out. Minus energy out. Energy in minus energy out. Now, there's a table that will give us the value. We'll come back and get a value for all this energy value. H to H single bond. Whatever you get, you write the value. Let's say 417. You multiply by 3. You get a new answer here. Plus, you do nitrogen to nitrogen triple bond. You write that answer. You add it to this. You get the energy in for breaking this bond. Then the energy out, they will only give you one of these. H to N to H, only one. So N to H, the value, let's say the value is 319. 390 times 3 times 2. 390 times 3, because there are 3 bonds. 1, 2, 3. There times 2, these 2 outside. So you can simply say whatever value is this single bond multiplied by 6, because 3 times 2 is 6. So you can simply say whatever value they gave you for N to H single bond, whatever value they give you, you can multiply by 6, because there are first of all 3 of this. 1, 2, 3, and then multiply by another 2. 3 times 2 is 6. So you can just multiply by 6, you get the energy out. So to get the energy change is simply to say the total energy you got here for your energy in minus your energy out. Is that okay? That's all you need. Now let's move on quickly. So we say, that's what we've explained this concept, okay? Now again we say that this process involves the transfer of thermal energy into and out of reactions mixture. The transfer of energy into and out of, that's exothermic and endothermic reaction. So for exothermic reaction, they give heat up to the surrounding, and endothermic reaction, they take the heat from the surrounding to themselves and they make use of it. The term used to describe these are what? The system. What happened in the chemical reaction, the system itself, the reaction itself that is taking place, and the surroundings. Okay? Whether energy is given to the surrounding or energy is taken from the surrounding. Anything other than the... Okay? That's all you need. The system and the surrounding. That's what you need in energy change. Now, the energy within the system comes from the chemical bond. The energy within the system is from the bonding itself, the bonding, the electrons, the atoms themselves that are reacting. They have their own energy. This energy within the system is coming from the chemical bonding between the atoms, okay, themselves, which could be considered as tiny stores of chemical energy, or what we call the internal energy in the system. The internal energy, both the kinetic energy and the potential energy in the system, they are called the internal energy. And this internal energy comprises the energies that are found in the system itself. Now let's take a look at exothermic reaction properly now. We've already explained them, it's just to run through it. Exothermic reaction, thermal energy is transferred to the surrounding. Yes, in exo, we gave example, we say like when you cooking, your cooking gas produce a lot of heat, and the heat energy is given to the surrounding. When you're cooking, a lot of energy is given to the surrounding, okay? And when you're burning piece of paper, when you're burning things, energy, combustion reactions, all of these are exothermic reaction. A lot of energy is given to the surrounding. It increases the temperature of our environment, okay? Exothermic reaction increases the temperature of our environment because it brings about heat energy to our environment. Now, this energy is transferred from the chemical energy that is stored, chemical energy store of the chemical system to the surrounding, and so the energy of the system will fall. In exothermic reaction, the energy of the system will fall. The energy of the system will what? Will fall, because it's giving heat to the surrounding. So when you give your energy out, that means your energy is dropped. Your whole energy is dropped. You that is giving it out, your whole energy is dropped. So the energy of the system in exothermic reaction will fall because the system has given a lot of heat energy to its surrounding. The system has given a lot of its heat energy to its surrounding. Now, what this means is that the energy change is negative. The energy change is negative. Why is it negative? Because the energy of the system has fallen below its value. So it's now negative. The energy change for exothermic reaction is negative. We use negative to connote or to show or to represent the energy of the system of exothermic reaction. Now, so the overall transfer is from the system to the surrounding. For exothermic, energy is transferred from system to the surrounding. For exothermic reaction, energy is transferred from the system to the surrounding. So if we say exo, if we talk about exothermic reaction, the energy is transferred from the system to the surrounding. So energy goes from system, okay, let's say this is system, to surrounding. Energy is transferred from system to surrounding. And then also the energy change, energy for the overall energy dropped. The overall energy will drop. Why? Because they give a lot of heat energy to their environment. So you say energy force in exothermic reaction, energy force. The overall value of the energy force, right? Because energy is given from the system to the surrounding. Or like endothermic reaction, energy is given by the surrounding to the system. Energy is given, so energy will increase, energy will rise in the case of endothermic reaction. But exothermic reaction, energy will fall because the system will lose its energy. The system will lose its energy and give this energy to the surrounding. The system will lose its energy in exothermic reaction, and the system will lose its energy and give its energy to the surrounding. So the energy in the system falls. The energy in the system falls. So the energy falls, and as a result of the fact that energy is given to the environment. Now, good examples of reactions that involve exothermic reactions where the overall energy falls, or you can say the system gives energy to the surrounding. Such type of reaction include number 1, combustion reaction, number 2, oxidation reaction. Whenever oxidation reaction takes place, energy is given to the surrounding. Energy is given by the system to the surrounding. Hence, the overall energy value falls below it said. Then we say it's negative. We say the energy change, the enthalpy change, or enthalpy. We use the word enthalpy change or energy change becomes negative. In exothermic reaction, you see minus. The energy values, they use negative. They use negative to show that the system has given energy to the surrounding. The energy value has fallen. The energy value of the system has fallen. Another good example of a reaction that involves exothermic is neutralization reaction. Remember, neutralization reaction is the reaction between acid and alkali. Reaction between acid and alkali. You've all studied this. Neutralization reaction. So we give example of this one. We say neutralization reaction, right? Neutralization reaction, combustion reaction, oxidation reaction. Neutralization reaction includes acid HCl react with sodium hydroxide, and then you produce salt and water. To produce salt and water, that type of reaction, it's a exothermic reaction. It's called exothermic reaction. Okay, we say hard warmers used in the winter time are based on the release of heat from an exothermic reaction. The hand warmers that we use in cold countries are using this principle of exothermic reaction because the heat energy is being released by the system to our environment, to warm our hand, to warm the whole environment, to warm our hand and warm the whole environment. Now let's take a look at this. Self-heating cans of food and drinks. The self-heating cans. You know, there are some cans that keep food always warm. Self-heating cans of foods and drinks, such as the coffee and the hot chocolate, also use the exothermic reaction in the base of the container. The base of the container, they use exothermic reaction. Now you can take a look at this diagram. This diagram is showing clearly an exothermic reaction. You can see the hotter than the surrounding. This has hot because this gives heat. Look at it. The system here is giving heat to the surrounding, giving heat to the surrounding, giving heat to the surrounding, giving heat in all directions, giving heat to the surrounding. The system is hotter than the outside. Inside is hotter, so it will give it all its energy to the surrounding, and the energy here will now drop. The energy inside will drop, and the environment around it will be warm. The environment around it will be warm. This is a diagram that is showing the transfer of heat energy outward from an exothermic reaction. This diagram is showing the transfer of energy outward by what? By exothermic reaction. Now let's take a look at the second one, which is called endothermic. Endothermic reaction. Endothermic reactions. Like we already explained, we say endothermic reaction is a reaction that takes heat from the surroundings. Here, they don't give heat to the surrounding. They take whatever heat is around the surrounding, they take it and use it and become warm up the system. Here, the heat energy, the energy change, the enthalpy change rises. The energy or the enthalpy change rises. It has not fallen. It gains more heat energy. The system gains more heat energy. The surrounding lose the heat energy it has to the system. The surrounding gives it the heat it has to the system. The system gets more heat energy in endothermic reaction. The system gets more heat energy. So we say plus. We use plus for the energy change. We use plus for the energy change in endothermic reaction. So we say in endothermic reaction, the thermal energy is taken in from the surrounding. So the temperature of the surrounding decreases. The temperature of the surrounding will decrease, but the temperature of the system will increase. The temperature of the system will increase. The temperature of the surrounding will decrease, and the temperature of the system will increase. Okay, so that's the first step. The second step is that this energy is transferred to the chemical energy store of the chemical system, so that the energy of the system will increase. We have already explained this. The energy from the environment or from the surrounding is being transferred to the energy of the system. So the chemical energy of the system will increase, and that of the environment will drop. So the temperature of the system will increase, the temperature of the surrounding will drop. The temperature of the surrounding will drop in endothermic reaction. Now the overall transfer is from the surrounding to the system. The overall transfer, in this case for endo, is from the surrounding to the system. For endo, I think we take a different, for endo. So for endothermic reaction, endothermic for endothermic reaction, okay, for endothermic reaction, what happens is that the surrounding gives the energy to the system. Surrounding gives energy to the system. Surrounding will be the one to give the heat energy to the system. Surrounding will give to the system. So the surrounding temperature will drop. Temperature of the surrounding will drop. Temperature of the system will increase. Temperature of the system will increase. So the system temperature will rise. Okay? The energy change will become positive. Here was negative. The energy change is negative for exothermic. The energy change was negative. Here the energy change will be positive. The energy change in endothermic reaction will be positive. The energy change will be positive. The system gains heat. System gains heat. System gains heat. And the temperature of the system increase. Gains heat. Gains heat energy. And then the temperature of the system also increase. Temperature of the system increase. Is that okay for endothermic reaction? The temperature of the system increase. So we say the temperature rise. Temperature rise. Or the system energy rises. The system energy rises, the temperature rises. So this is for endothermic reaction, okay? Now all the heat in the surrounding will go into the system because the surrounding will become cooler. Okay? This one originally the system was cooler. So it gets all the heat around from the environment to itself. Now let's give example of reactions that involve endothermic reaction. Reactions that involve endothermic reaction. Good example is electrolysis. Electrolysis, and then another example is thermal decomposition. So electrolysis, all the electrolysis that you've done, they undergo what we call the endothermic reaction. That thermal decomposition, the breakdown, like hydrogen peroxide to hydrogen into water and other elements or oxygen. Then anytime like calcium carbonate, breaking of calcium carbonate into carbon dioxide, calcium oxide, and calcium oxide and carbon dioxide. The breaking of calcium carbonate is a thermal decomposition. Any thermal decomposition reactions that takes place is an endothermic reaction. Is that okay? And then the first stage of photosynthesis also is an endothermic because it takes the sunlight energy. The first stage takes the sunlight energy. The first stage of photosynthesis takes the sunlight energy into itself and make food, produce food. So that first stage of photosynthesis is also an endothermic reaction. Now we say spot injury treatment often use cold pack based on endothermic reaction to take heat away from the recently injured area to prevent swelling. Okay, when you playing sport, you see sometimes they bring ice block to massage the spot in order to avoid swollenness. This is because it's an endothermic reaction. It's an endothermic reaction that is taking place. Okay, it will give energy from the surrounding to the place in order to avoid swollenness. Okay, now let's take a look at the energy diagram for both exothermic and endothermic reaction. The energy level diagram. Okay. Let's quickly, we will round up with this one, the energy diagram for today, okay? Let's round up with this energy diagram. Okay, so we say reaction pathway diagram is what we call the energy diagram, and the graphical representation of the relative energies of the reactants and the products in chemical reaction. What we have described, we use the energy diagram to explain them. The energy of the reactants and products are displayed on both the y-axis and for the reaction pathway and the x-axis for the time it takes for the reaction to take place. Now, the difference in height between the energy of reactant and the energy of product represents the overall energy change of the reaction. The difference in height, you see, this is reactant. This is the energy of the reactant for this reaction. This is an exothermic, okay? And this is the energy of the product. The difference in height, that's this one. The difference in height tells the overall energy of the system, tells about the overall energy of the system. You can see the energy here is lower for exothermic, is lower than the energy of the product, okay? Because this one has given all, the system has given all its energy to, the surrounding. The system has given all its energy to the surrounding. So there's a fall, you see? There's energy released, okay? So there's a fall in energy, there's a fall. So it's negative because the product is lower than that of the surrounding, you see. So there's a fall in energy. But the overall energy here, the reactant, look at the energy of that of the product is higher. There's a rise. The system gains more energy, right? Because it gets energy from the surrounding, gets heat energy from the surrounding. The system gains more energy and absorb energy. See, energy is absorbed. So you can see there's a rise. This one, there's a fall. Exothermic, there's a fall. So when you're drawing, remember rise and fall. In exothermic, there's a fall. So the product has to go down more than the reactant. Then in endothermic reaction, the product will stop below the reactant. The energy of the product will stop below the energy of the reactant so that you can have a rise in the energy. Okay, so this plot of energy against the progress of reaction or reaction pathway. Okay, so this is what we have, and the arrows are showing the energy, the type of energy, overall energy of the system. Now, the initial increase in energy represents the activation energy. The initial increase is the activation energy, meaning from here to here, this place. The energy, activation energy is the minimum energy that the colliding particle must have in order to react, must overcome. The energy you have to overcome in order for the reactions to finally to be able to take place. So the initial energy you have is called the activation energy, the energy in this place. Okay, the activation energy. Once you overcome that energy, then the product will be formed. Okay, the greater the initial rise, the more energy that is required to get the reaction going. Okay, the greater the initial rise, the more energy you need to keep the reaction going. Okay, so that's what we have for today. And next time we're going to look at the enthalpy, the calculation itself, which I have given you the formula. The calculation which I have given you the formula is what we're going to look at in our next class. Is that okay? Is that okay?
Yes.